Hi, I'm Drumil, and today I'm going to walk you through the diffusion models for image generation, specifically how systems like Stable Diffusion and DALL work under the hood. If you've ever typed a sentence and watched an AI generate a photorealistic image from it, diffusion models are the engine behind that. So by the end of this video, you will understand the core idea, the architecture, and what makes latent diffusion the backbone of the stable diffusion and so efficient. So let's start with the big idea. Take this stickman image, which is a clean image. So what's actually happening in the forward process is we're taking the image and we are adding the noise gradually until we're getting pure static. So there's no learning here, it is just math. The reverse process is where the actual magic happens. We train a neural network to look at a noisy image and predict how to remove a little noise. So doing that well enough, we can start from a pure random noise and denoise it into a real image. So the game is simple. We destroy with noise and then we learn to undo it. So we define a network as the epsilon hat of the particular noisy image at a particular timestamp t. Our goal is simple. We want our output to be as close as the actual noise, and we define a loss function as the mean square error of the actual prediction to the actual noise. So not all the time steps are equal. A noise schedule controls how much noise we add at each time step. A little noise early on, almost pure static by the end. As the curves, we can see the signal starts high and then it drops, whereas the noise is starting low and then it rises. The network receives the time step t as input, so it knows how noisy the image is. That matters. Denoising a slightly fuzzy image is a completely different job than denoising the pure static one. So this is the architecture of the unit, which has the same idea of the segmentation adapted for the generation. We have encoders which help us in downsampling the image and extracting the features at smaller and smaller scales. We have decoders which upsample back to the full resolution. Then we have this skip concat, which helps us in skipping the connections and linking the matching layers, which helps us in preserving the fine details. Then we have the bottleneck, which adds self-attention so that the model can reason globally and not just locally. Then we have timestamp t, which gets injected into every single block, so that the network knows how noisy the input is. And finally, to conclude, the noisy image and the timestamp, it goes in, and what the out so the t gets injected at every single block, and what we get the output as it is the epsilon hat, which is the predicted noise, which we saw in the previous slides too. So far, our model generates random images. To go from text to image, we need conditioning. So we take a prompt, which is a stickman riding a rocket. We pass it through the Clips text encoder to get an embedding vector. That embedding gets fed into the unit through the cross attention, and the image features are the queries. The text embeddings are the keys and the values, which means every part of the image can attend to the relevant words, and the text literally guides where to put what during the denoising. So here's the problem. Diffusing 512 by 512 images is really expensive because of the amount of values we have to deal with and the hundreds of steps we have to go through, which is really expensive. So Stable Diffusion has a trick, which is to compress the image first, and later a VAE encoder squashes the image down to a tiny latent, which is roughly 48 times smaller. So all the denoising which takes place is happening here, and the unit never touches the entire image. And later, once we have a clean image, clean latent, the decoder reconstructs the full resolution image. And the reason is Stable Diffusion runs on a consumer GPU